The next measurement we shall be looking at is at resistance. Resistance in an electrical circuit resists the flow of current and therefore can affect the voltage. Let's take a water analogy, a tap and a bucket. The resistance of the flow of water depends on the tap. As an example, we could open the tap just a couple of turns and the water will flow. This means we have reduced the resistance to the water. By shutting the tap reduces the flow of water until no water can flow, or we have increased the resistance to the water. If we open the tap a few more turns, then the water will flow much faster. Thus the resistance to the water is less. Let's take a 12-volt battery, a couple of crocodile clips and an electrical resistor. If we take a multimeter with two probes, then switch the meter to read voltage, we can see by measuring across the resistor the voltage, which in our example is 12 volts. A single resistor connected in this manner has very little influence on the voltage. This can change if we add a further resistor. This second resistor has the same resistance as the first, so the total voltage is now split. It is not that important for us to understand exactly what's going on here, just that the resistor will restrict the flow of current. Without this fundamental law of electricity, certain events could never have happened.
I'm going to step off the limb now. That's one small step for man, one giant leap for mankind.
Our only interest here is infinite resistance and no resistance. We can relate this back to our tap. If it is either closed, so no water can flow, or fully open. Electrical resistance is measured in ohms. The more ohms we have, the greater is the resistance. This is the sign for ohms. On this meter we can see we can measure in different scales. Up to 200 ohms, 2000 ohms, 20 kilo ohms or 20,000 ohms, 200 kilo ohms or 200,000 ohms, and finally 2000 kilo ohms or 2000,000 ohms, which is 2 mega ohms. The way we can relate to this is at 2 mega ohms our tap is just being turned on. In other words, the resistance is very high, while at 20 kilo ohms we have opened the tap much wider, and at 200 ohms the tap is almost fully opened. If we select the range within the resistance, the meter always reads 1 without the probes touching. 1 means infinity or open circuit. In other words, current cannot flow from the red probe to the black one at this time. With the 200 range selected and touching the probes together, the resistance shows about 1 ohm, very little resistance, or a closed circuit. So what would we expect a good fuse to be? Here we have a selection, 1 amp, 3 amp and a 13 amp. Leaving the meter setting at 200 ohms, we shall place the probes on the metal contacts of the fuse. As we can see, the resistance is very low. This makes sense, since if the fuse has blown, then the circuit would be dead. It would have a resistance reading of infinity. Once again, it means that current cannot flow from one probe to the other. We can also use the resistance range for fault finding on the power switch found on most PC cases. On economical cases, the front power switch can be prone to sticking either on or permanently in the off position, thus rendering the computer with no power. This can be checked in the following manner. Here we have the front panel connector on the motherboard. We can see the power switch is a 2-pin connector. If we turn this over, we will find the exposed contacts. Now if we place the meter probes into the connector, then the meter is showing 1 or infinity. If we now press the power button on the front, then the reading of the meter will change to less than 1 ohm, showing that the power switch is working satisfactorily. However, if the meter reading did not change, then we can assume that the power switch is not working as it was designed to do.